So I'm going to carry on where we left off. I think most of you managed to get to the solution. Now we've tested the assumptions. There's many ways to do an ANOVA in R, and so I'm going to teach you a couple. And why this matters will become clear when I discuss the different sums of squares, which you might different ways in which you can have types of sums of squares. So there's many ways to do it. I'm going to run you through some solutions. I'm going to tell you how they're different. So one of the easiest ways is to just do AOV, which is analysis of variance. By now, this should sort of look familiar. So we have the dependent variable, we have the tilde, the independent variable. We tell it which data frame to use, and then we do a summary. And this is where you'll get your F test and your p-value. Yeah, and it uses this lovely type of star notation, so you can go star hunting for significance if you wanted to. So you can see this is a highly significant effect here between the groups in openness to experience. So we can also make ANOVAs, do ANOVA in a different way. We can use LM, which stands for linear model, and ANOVA, because ANOVA is regression, R sort of set up that you could use LM as well, which is a linear regression model. So in this case, the output looks slightly different. Oh. So here it's printed it like a regression model. So it's not printed this overall f-test after, but it's printed estimates and it's printed t-tests associated with each parameter estimate. So there is no f-test. So it prints the parameter test, but you are interested in after this f-test, which you need for your statistics report. So in order to do that, you do ANOVA of the ANOVA to object, and then you have this type of thing. And they should look quite different, or quite similar, sorry. They shouldn't look any different. So 15.05 and 15.054. So it's just printed an additional decimal. So you get the same conclusion if you were to use a linear model or AOV to get to your ANOVA solution. It's just that one is based on regression, supposedly, and one is based on analysis of variance. But one of them, well, they're mathematically equivalent, so you can reset everything from one into the other. So for your reference, you can also use drop one to get the same type of info. So you will also get the sums of squares and some additional junk if you want that. So don't worry about it for now, but I'll tell you in future about information criteria, like the Aki-Aki information criterion. It's basically a fit statistic as to how well your model fits the data, and you can use that to compare models. So if you ever need that, you can use drop one. So this is mostly just for your reference, and gives you some additional things. But your best bet for if your supervisor is really an SPSS guy or girl, he's very much into SPSS style results. The best way to replicate that would be using the easy package. That's really mirroring what SPSS does. Again, in this case, it won't be much different. You can see that the f-test is 15.05, but then put some additional decimals, but 15.054, you remember, and it's this it's significant again. In this case, you don't get multiple stars; you just get these stars. So it looks slightly different because in this case, we put the data first. We say this is the DV. You actually have to say this is the DV. You have to tell it an ID variable because it can handle data. It can handle more complex data sets where you, for example, have multiple cases per individual. So think about a within-between design in ANOVA. So that's why you have to tell it which variable is the ID variable. And then you tell it the between ANOVA factor, the group factor, and then the next bit will be detailed is true, which prints you a detailed summary. And as a bonus, it prints you this Levine's test. So forget about all the things which I just told you about how to run a Levine's test. You can also get it this way. Yeah. So, and this should sort of replicate what we had before. I think it does. I recall was 0.18 for this Levine's test. Yeah, so all the information is there. So you might have spotted that there's something printed here which is guess. So or guess. What's this guess type of thing? It's in a measure for effect size. So as a bonus, it also prints the generalized eta squared, and that's the Greek notation. So there's also partial eta squared. If you want to read more, you can click about those. For very simple designs, your partial eta squared will map onto your generalized eta squares. For more complex designs, it will not. So you probably also wonder how I do Greek symbols. So you can click here to do to find out more, or you can check the markdown for this lecture, because sometimes you will need a Greek symbol also in your write-up. So that's how you do Greek symbols. So there's also, if you're up for a challenge, you can also figure out how to do omega squared and partial omega squared, which are other measures of effect size. So there's lots of debate currently in the academic community as to what is the best possible way to express effect sizes. And some people, like your supervisor, they might prefer omega squared. And so this is how you would go out and about and calculate omega squared. And if you were to write up your results, then you would write one way ANOVA showed a significant effect of cultural group on openness to experience. You report the F-test. I perhaps should have put the comma still here, but you report the F-test, the p-value, and an effect size measure. That would be the appropriate way to report it in text. Yeah. Now the beauty of this is that we can actually also make tables directly for a report. So in SPSS, you would have to do lots of copying and pasting to get sort of results formats. And in this case, we just call a package called APA tables, which you should install previously. Then we can say apa.aov.table. We can call the ANOVA effect, things because it needs the ANOVA object. And then we can save it as a table. And you can sort of see what it will look like in this type of output. But let's see if I can show you also from my results. So lecture 3. So this is hopefully, if it works, sort of what it will look like. So that will generate a table straight up for your report if you want to insert a table in your report. Blame Microsoft Word for being slow. We're getting there. There we go. So this is sort of what it will look like. So we'll have made a formatted table. It's probably a little bit zoomed too much. Let's see if I can reduce the zoom. It's 163%. So it will have made this nice table. If you had labeled this correctly, it would have been factor group or something. Sums of squares, degrees of freedom, mean square, f-test, p-values, partial eta squared, and a 98% confidence interval for partial eta squared. And you can modify some of these things to your liking. So you can say, probably you can say 95%. You can tweak some of these things if you need to. See, so that's again somewhat of a time saver. Whereas perhaps in SPSS you would have had to copy manually all those results into a table. So, but here you would have a single table already produced for you in a Word document, which you can then copy and paste. Okay. The reason why we're teaching you also is because this avoids errors, because the likelihood if you manually copy over things that you will make an error or that you will make a rounding error of some sort will go up as you do these type of things over and over. Yeah. So that's hopefully, I'm sure you still hate R, but hopefully I'm convincing you more and more as the benefits of things, especially if you have to do for the next 20 years, if you have to write statistical reports, having things which format tables for you over and over in a standardized format will save you some time. Any questions so far? Let's go back and have a look. So that's in an easy way printed out as to what it looks like in text, and it will then generate this thing which will live in your working directory. So post-hoc difference tests, you remember also when you're doing ANOVAs, you want to find out where the differences lie between these groups. And so you get usually when you get a significant overall test, perhaps here it doesn't matter too much because you only have 3 groups, but imagine you have 20 groups. You will have an overall significance test, which is significant, but you want to find out which groups are really different from one another. And we do that via post-hoc tests. We can call our first ANOVA object, and we can do Tukey AHD to get the Tukey comparisons. Again, for all the terminology, you have to go back to your undergraduates. It's all the type of things which you have done. And so here it will print the differences. It will print you the lower and the upper confidence interval, and it will print you the significance thing. So there is no significant difference between Asian internationals and European Americans in their scores in openness to experience, but there is a difference between Asian Americans and the 2 other groups in their openness to experience. Yeah? Everybody sort of with me and understands? So you have probably heard of corrections. So Tukey is quite lenient. So why do they exist? Why do you have these corrections for these post-hoc tests? Does anybody remember? Why we, so you might remember Bonferroni or SIDAC or all these other beasts. So you remember why you were supposed to do them? The answer has been given in the first part already because it's type 1 error again. So if we were to test things over and over, and some of these comparisons will be significant by chance. And so you want to use them sensibly, but you can probably get rid of Bonferroni because it's really, really stringent, and people have argued against it in biology and medicine. But you should use them in a very sensible way. So sometimes it makes sense to correct for things, but for example, for exporter analysis, you don't want to overcorrect, and then the Bonferroni correction might be too stringent. So go back to your undergraduates things to sort of see how you can do all those corrections. And there's all sorts of options to do changes so you get the type of results different. We can even make a prettier type of table if we want for this post-hoc comparisons. So in this case, I call a package called Broom and a package called Stargazer. What does Broom do? Broom takes a result and will turn it into a data frame by a simple command which is tidy. So if we do tidy underscore result key, it will do this. And then Stargazer will make a table for us from that data frame. And so just taking this object, not having a summary because otherwise it will calculate the means and standard deviations of everything, make it an HTML file and save it as an HTML file. Now this might not work because it doesn't like it when I bind things together, but it might have done it nonetheless, and otherwise I have to do it again. Let's see if it loads. There you go. So this will have made an HTML table. You can change in the data frame because it's a data frame. So here it's just print all the decimals. So you know your commands from rounding, so you can make that a prettier data frame. But there it will make a data frame, and if I had changed the labels to make this something more sensible, you would have a prettier result. And again, if you do this over and over, you can then take this is HTML, so you can just copy and paste that into your Word document. Again, it will avoid errors that you make when copying your results from SPSS or manually copying them into Word documents if you first make it into an object from R. Yeah. So that was post-hoc tests. We can also ask it to make means and SDs. So we can, again, this is an alternative to our post-hoc summary. We can ask APA tables. We can use this command to give it a data frame to basically make a table with cones, Ds, and means and standard deviation. We tell it which the independent variable is. We tell it which the dependent variable is. We tell it the data frame. We give it a file name. And then we can say, show the confidence interval. Do I want a landscape type of table or a portrait type of table? In this case, especially if you have lots of things to print, you might want to have a landscape table. And you can also number the table if you want to. So you can say this has to be table number 1. Let's see if we can find this here. Again, it will depend how fast things is. So this will make a table with a caption on it. It will be APA style format. It will print the means and standard deviations, and it will print the cones D values for the comparisons. So that's quite nice, no? And so it tells you also which type of formulas it used and provides you some additional information as to what the 95. So these are 95% confidence intervals for that. And again, looking at the command, you can tweak certain things. And again, it will sort of avoid that you would have to manually copy over the means and standard deviations into tables. Yeah. So hopefully, more and more, I'm trying to convince you that this is quite a useful thing to do and to have, because it will save you some time if you have to make lots of reports where you have to do this. Any questions so far? So again, this will live in the document where your R Markdown script is living if you don't say where it has to write it away. So that was APA tables. So what I'd like you to do now yourself is to run an ANOVA with ES extroversion. It can be any type of ANOVA, and to conduct a post-hoc test and export it either as I've done via Stargazer as .html or using APA tables, which is cones D type thing. So just do the same steps as I have. You don't have to do all 3 versions in which you can do an ANOVA. Just pick one. So pick AOV or LM or easy to do it, and then conduct the post-hoc tests and export those as either HTML. I think for the post-hoc test, it's actually best that you use AOV, that first thing which I used, and export them. Okay.